Hello. Yes. So, greeting. Welcome today for the week 5 discussion. As there is a lag in these sessions, today we'll be discussing driveline and transmission corresponds to syllabus of week 6 and a little bit of week 7, so that we are on pace with the NPTEL weeks. So let me switch to pen paper. Today will be a tutorial session where we will be solving some more problems. So the first problem for today will be find the better choice of drive. So we can have forward wheel drive or front wheel drive or rear wheel drive for the following vehicles. So let's look at vehicle 1. Vehicle 1, the weight is 1000 11,505 kilograms. Okay, we're writing the weight, so it's in newtons. Wheelbase is 6.28 meters. L1 is 1.066 meters. H is 0.565 meters. This is the height of the center of gravity, and rolling resistance coefficient would be 0.015. So since L1 is this, L2 would be capital L minus L1. This would be 1.614 meter. So we know the height of the center of gravity, rolling resistance coefficient, and the length of CG. Let's look at in case of front wheel drive, what is the maximum force we are getting. Maximum force we are getting will be mu into W in bracket L2 plus Fr into H over L plus mu into H. So we will be taking for this discussion mu equals to 0.8. That is the friction coefficient. So 0.8 into newtons into L2 is 1.614 meters plus 0.015 into H is 0.565. Divided by 2.68 meters, that is the length, plus that's the wheelbase, and friction coefficient 0.8 into 0.565. So F max in this case would result in 4768 newtons. Now let's do the same calculation for rear wheel drive. Rear wheel drive, we'll have F max equals to mu into W L1 minus Fr into H divided by L minus mu into H. 0.8 into 11505 1.066 meters minus 0.015 into 0.565. So the maximum force after running this calculation is 4369 newtons. So if we were to compare F max in case of front wheel drive is greater than F max at in case of rear wheel drive. This implies we can say that in this case a front wheel driven car instead of car, let's write vehicle, is a better choice. Oh, so these are the problems on driveline and transmission. Okay, I'm writing them down as we go along. Okay, this corresponds to your sections on powertrain analysis and transmission, right, and automotive powertrain. Okay, so let me continue. So we'll solve the same question again for a different vehicle, right? So part B, that is vehicle 2. So here the weight is 5880 Newton. So wheelbase is 3.025 meters and L1 is 2.102 meters. This makes L2 as 0.923 meters. The height of center of gravity is given as 0.258 meters and rolling resistance coefficient is the same. So in case of front wheel drive, the maximum force we can get is mu into W in bracket L2 plus Fr into H divided by L plus mu into H. Okay, so if we were to substitute these values again, mu is 0.8, then we have 5880 as mass of the vehicle in bracket 0.923 So this calculation results in 1349 newtons. Okay. So if we were to take a look at this formula for F max, it depends on following things. First is it depends on friction coefficient, right? Then it depends on uh, the vehicle attributes, such as center of gravity position, that is denoted by L1, L2, and H. And another attribute is weight of the vehicle. So during vehicle's operation, the CG would change because the loading condition will change, and it will also influence the weight of the vehicle. So when we do design, we kind of take nominal values for these things so that we can decide on a front wheel drive or a rear wheel drive kind of a system. So for this particular vehicle now, let's move on to the rear wheel drive. So here the maximum force would be 0.8 into 5880 Newton. L1 is 2.102 meters. 2.102 meters minus 0.015 into yes, Abhishek, I'll come back, give me a second. 0.258 minus 0.8 into 0.258. So this comes out to be 3502 Newton. So yes, we were discussing a question. We are discussing today questions on driveline and transmission. The first question we are dealing with is find the better choice of drive, forward front wheel drive or rear wheel drive for the following vehicles, and we are expected to take the friction coefficient mu as zero point 0.8. So we have been given various attributes of the vehicle like the weight of the vehicle, the wheelbase, that is L, okay. Weight of the vehicle, the wheelbase, and the position of CG from the front wheel. So we can calculate position of CG from the rear wheel as L minus L1, and then height of the center of gravity, and we have also been given the rolling resistance coefficient. So looking at the maximum tractive force F max, which is calculated this way, we calculated for front wheel drive and rear wheel drive using the same vehicle parameters. So for the first vehicle, we concluded that the maximum force, maximum longitudinal tractive force for front wheel driven vehicle is higher than that of a rear wheel driven vehicle. So in this case, a front wheel driven vehicle is a better choice. Then we did the same calculation for another vehicle, right? And we can see here that the maximum tractive force for a front wheel driven car is less than the of the rear wheel driven car. So in this case, a rear wheel driven vehicle is a better choice. Now looking at third vehicle, in this particular case, the weight is huge, right? And the wheelbase is 4.2 meters. Okay, this formula is not there in the recorded videos. All right. Okay, that is not there. Then let me quickly check my driveline and transmission notes. We can certainly find a place where that is derived. Then we can discuss the derivation here, and then we can come back. Okay. So let's look at the forces acting on the vehicle. All right. It's better if I can draw this diagram while explaining each of the force. So let's take it here. All right. So let's go to derivation of this. Yeah, I can share the notes. So, so let us consider this angle as theta s, and let me draw two wheels. Okay, so this is the CG, right? At this point, we will be, this is the weight of the vehicle. This is the direction in which the vehicle is accelerating. So this will be the uh, equivalent force, we can say. Then we have this, resisting force RA, which is being applied at height HA. That is because of the aerodynamic drag. If you are doing something else, then you have a resistance due to drawbar pull, which is HT. Then you have the forward driving force, and you have rolling resistance force on both the wheels. You can call this length as L1 and this length as L2, and the total length is you can call as capital L, which is the wheelbase. Okay, so the loads are, there is inertia, aerodynamic drag, so we can write the equation of motion as m into x double dot equals to w by g into a, right? That is equals to, so forward driving force on the front wheel, driving force on the rear wheels. Okay, then we'll start subtracting the resistances. First is the aerodynamic drag, then you have rolling resistance at the front wheel, rolling resistance at the rear wheels. You have the drawbar pull RD and the grade resistance. Now what we can do is we can combine these terms for the attractive force, right? We can replace this by F. We can replace these two, that is the rolling resistance, as RR. This would result in an equation, the force, which is uh, W by G into A plus RA Okay, so now what we can do is we can consider these points, okay, and take moment about them. So if we take moment, about point of contact of rear wheels. We get the following equation after a little bit of algebra. WF is 1 over L. Sorry, yeah. So we'll get the normal load on front wheels, WF. So we have that minus or plus depending upon we are climbing up or coming down the slope. And if we take the moment about the point of contact of front wheels, then we will get the normal load on rear wheels. Okay. If we were to simplify these equations by assuming that my HA and HD are H and grade angle is small, then we can write cos theta as 1 and sin theta as it is. We can write WF as W into L2 by capital L. Yeah, minus. Okay, so what we see inside this bracket is essentially this expression, but without the uh, rolling resistance term. So we can write this same expression again with net traction force. So So let me label this equation as 1. We can write WF as, sorry, F minus RR, rolling resistance, and okay. Which screen is visible? The screen I'm writing is visible, right? Yeah. So I'm just trying to help with the drawing and little bit. Now I think we can go back to the slides one more time. And yeah, this is where we are, right? Using the expression for net tractive force, we can get the WF and WR, that is the normal load on front and rear wheels, in terms of the tractive force, rolling resistance, and the vehicle attributes like weight and CG position. Okay, so if we want to obtain the for a front wheel driven vehicle the maximum tractive force, we can substitute in F max as mu into WF. Right, we are limited by the tire road friction coefficient, that is mu, and the normal load acting on that. Okay, so then we can substitute F max as mu into WF, which equals mu into this portion, which is essentially the expression of WF which we derived. Here you can substitute, we'll introduce a term called FR, which is the rolling resistance coefficient. Okay, this rolling resistance originates because of the, the elastomers, or roughly speaking, rubber in the tire, which constantly goes loading and unloading. And because of this loading and unloading, as the tire moves, the strain energy gets built up and gets released. But in doing so, there will be some residual energy which goes out as heat, right? Which is termed as the rolling resistance. And this rolling resistance is written as Fr into W, which is defined in terms of the rolling resistance coefficient and the load acting on that particular tire. So after substituting uh, the value for rolling resistance as this, the final expression for F max comes out to be this for a forward uh, or a front wheel drive vehicle. Similarly, we can do it for rear drive vehicle. Right, the maximum tractive force is mu into WR, which leads to this expression which we have been using uh, in the assignment or in this tutorial. So let us go back to, so this is how we can derive the formulas. So let's go back to the vehicle 3 again. So this is the weight of the vehicle. Wheelbase is 4.2 meters. So L1 is 2.7 meter. That gives L2 as 1.5 meters. H is 1.45 meters, and rolling resistance coefficient is 0.006. So for a front wheel driven car, vehicle, F max is mu into W in bracket. Okay, if we substitute the numbers in this case, we get answer as 24274 Newton. Similarly, if we do the calculations for a rear wheel driven vehicle, this comes out to be right. So in for this particular heavy vehicle, we have F max at front wheel drive is much less than F max at rear wheel drive. So in this particular case also, is better suited. Okay. Uh, I think, yeah, Ronak, I think this will be taught in week 7, if not already taught. Uh, no, the formula will not be given in the exam. I think you will be expected to know at least the final formulas. I would recommend that you can have one sheet of paper on which you can write all the relevant formulas for each of things, so that it becomes easy for you to revise before the exam. Right. Again, I have never given an NPTEL exam, so I don't know how that exactly is. So, till what point the things are discussed? We go here. So, is the gearbox portion discussed in the class in week 7, wherever you are? Okay, so due date for week 6 is tomorrow. Oh, that is why the week 7 part is not done yet. All right. Okay, anyway, we'll continue with the discussion so that it is helpful. Mhm. So the next problem we want to have a discussion on is that of a 4-speed gearbox design. Okay, so we are saying that number of gears are 4, weight of my vehicle is 12,000 newtons, maximum engine torque is 100 newton meter, maximum vehicle speed is 100 kilometers per hour, which is 27.78 meter per second, and omega max is given as 2 pi over 60, so into 3000, so it's 3000 rpm. This gives it in radian per second. So yeah, kindly make sure whenever you are doing your homeworks, units, try to keep them in SI units. So this will be 314.16 radian per second. Okay. Right. So essentially, we are trying to solve this problem where we are saying that a vehicle weighing 12 kilonewton needs to be equipped with a 4-speed manual gearbox. The engine develops maximum torque of 100 newton meter. The vehicle should reach its maximum speed of 100 kilometers per hour when the engine is running at 300 rpm. The vehicle should have gradability of 20%. It is also required that the fourth gear corresponds to direct drive. What does the direct drive mean? It means that the engine is directly connected to the wheels without any kind of uh, gear reduction or upping in between. That is, the RPM of the engine would end up being the RPM of the drive shaft. Then we are taking the radius of wheel as 0.3 meters and we are considering transmission efficiency of 95%. Right. We are asked to determine the gear ratio of the lowest gear, the highest gear, and the final drive. With the available information, determine the gear ratios of the intermediate gears. You may neglect wheel slip ratio, rolling resistance for obtaining these values. So, uh, this is the question we have, and we have been writing the requirements here. So, we have been told that gradability is 20%, right? So, this is 0.2, which is tan of theta s max. So, maximum gradability is 20%. So, the maximum value of theta s happens to be 11.31 degrees. We have been told that it is direct drive. So N4 will be 1. Okay. Radius of wheel is told to be 0.3 meters. Transmission efficiency is given at 95%. And we have been advised to ignore the wheel slip ratio as well as the rolling resistance as 0. Okay. So with this given information, Just 1 second. So let's quickly go through some transmission uh, discussion. So yeah, this is what the gradability condition you are talking about. So the vehicle has to be designed so that it can climb up. What is N4? Yeah, N4 is the final gear ratio. Let's go through these few slides so that we fill in the gaps. Okay, what is gradability? It is the maximum grade that a vehicle can negotiate at a given steady speed. So at steady speed on a grade, we have to overcome, that is the force at the wheels has to overcome the weight component due to the grade, that is W sine theta, the rolling resistance RR, and RA, the aerodynamic drag. For small grade angles, we can consider sine theta is almost similar to tan theta, uh, and G equals to tan theta, that is the grade definition. And if we equate this from above equation, we get G equals F minus RR minus RA by W. So this can be used to determine the maximum speed that can be reached at a given grade. Okay, then we have something called wheel slip ratio, that is here it's defined during drive as R omega minus V by R omega. So the relationship between the engine speed and the vehicle longitudinal speed in the ith gear is given as this. So we are essentially rearranging the equation written above. Okay, if we rearrange this equation, then we get V in terms of radius, wheel speed, and wheel slip ratio. Okay, so okay, so for the ith gear we have NTI into ND. So we say that chosen speed, the highest gear is chosen in a way that the desired maximum vehicle speed can be achieved with appropriate engine. Okay. So let's go a little more up. Okay, this is what we discussed, right? Tractive forces and all. So if we put NTN equals to 1, right? In our case, we have been asked to put N4 equals to 1 for the direct drive. Then we said that it is the highest gear. Yeah, so if we put this as 1, we can calculate ND by taking Vmax here. Then we have requirement of the lowest gear. The lowest gear is selected in a way that you should be able to climb the steep gradient. Right, here we have been given requirement of 20% uh, without any spin. So if we neglect the wind resistance, the aerodynamic drag, because our vehicle speed is 0, we can say that W sine theta S max should be F max minus FR into W. Right. So we have to overcome the rolling distance. So then the gear ratio of the lowest gear is given by this expression, where we are taking TE max as the maximum engine torque. So in our case, it has been given as 100. And then uh, we are saying that the intermediate gear ratios should follow geometric progression. So the idea is that uh, we want to have the engine operate in the same range of speed for each gear. If we were to consider, uh, yes, I think I can share this PDF. It should be publicly available. Uh, it might take some time, but it will be available. Anyway, it's the same as the NPTEL notes. What you can download as well. Yeah, so we can say that NT2 by NT1 it will be same as NT3 by NT2 will be same as NT4 by NT3, right? Which is omega T by omega max. So we can define that as uh, the constant kg, which is essentially cube root of NT4 by NT1 for a four speed gearbox, right? So we can keep on substituting in terms of kg, and we will get the expression for this. So this is the problem we are now looking to solve. So from requirement of maximum speed, we can say this. So we are neglecting lambda, and we are saying that NT4 is 1 and Vmax is 27.78 meter per second. So this would result in answer of 3.393. Okay. So this is the first information we are using. Then we are saying from the requirement of gradability. Right, from gradability we have to pick it up from standstill, which we will be doing in first gear, right? So sin theta is max is Fr into radius. So if we substitute the values, and we are neglecting 11.31 degrees, We are neglecting the rolling resistance coefficient. Sorry, 2.19. So as we discussed, we can get the factor kg as cube root of, so nt1 is known. You can write nt2 as kg into nt1, which would come out to be 1.686, and then nt3 would be kg into nt2, 1.299. Okay. So N1 we have, N2 and 3 we have, and N4 was 1 because we are told that it's direct drive. Okay. Why neglect lambda? Because that will take you into the understanding of tire and tire model, and for this particular calculation, we need not go in that direction. Anyway, we have this as 1 minus lambda, right? So if you are driving in not too extreme conditions, right? If it is by and large at constant speed, uh, then in such a scenario, your lambda is pretty low anyway. But in case where you are uh, accelerating very rapidly, or you are braking uh, in a situation where ABS is required, anti-lock brake system is required, in such a case, lambda becomes significant. So the lambda gets related to the tire road friction coefficient with mu lambda curve, and if you want more relationships into that, that is what will pull you significantly more into vehicle dynamics, which we intend not to go for this particular discussion. As you might be aware, uh, NPTEL also has a follow-up course on vehicle dynamics, right, by Professor R. Krishna Kumar, which are excellent set of videos, and which is a follow-up course in Department of Engineering Design after this course. So generally, this course is taken by our fifth semester undergraduates, followed by vehicle dynamics in their sixth semester. Right, so it's kind of continuation. We are neglecting lambda here because we do not want to go into discussion of how the wheel slip ratio works and how to calculate wheel slip ratio. Right, it's more of a dynamic quantity, whereas the relations which we are working with here are algebraic relations. Right. So that is the intention why we are neglecting lambda. Yeah, I hope that answers the question. So are there any more questions? Okay, let's continue with our final bit on discussion. So we want to do the same kind of thing for a 5-speed gearbox instead. Okay. So N here is given as 5. It's the same vehicle. So I'm just writing down the given information one more time. 314.16 radian per second. So here also the grade is given as 0.2. This implies theta as max is 11.31 degrees. Right. Fourth gear is given as direct drive. Transmission efficiency is 95%. Yes. So we have defined kg as nt2 over nt1. Right. These are in geometric progression. Right. So let's try to uh, work with maximum speed condition. Right. We said that maximum speed is so here we do not know what NT5 is and what ND is. So we'll keep that as a product. Okay. Now we take another condition, right? The gradability condition. Or gradability requirement, we can write for the first gear as so this will give us NT1 into ND. Okay. So if we, since we do not know three things, and we have two expressions, we can divide these two expressions to get rid of ND, right? So we'll be left with NT5 divided by NT1. Okay, this will be omega max 1 minus lambda into T max eta T over V max. Okay, if we neglect lambda and FR, we have this ratio. Okay, let's substitute the values to get NT5 by NT1. So we get NTS over NT5 as 0.4565. This is also kg power 4. This implies we will get kg as 0.822. So since NT4 was 1, we will get NT5 as kg into NT4, which is 0.822. Then we can get NT3 as 91 as NT2 over kg equals 1.8. So since now we know NT1, we can finally calculate ND as okay. So yes, so that way we have gotten all the design parameters for the transmission. So as per the timeline, week 6 assignment is due day after tomorrow. So, and we have discussed week 7. So week 7 starts with transmission matching and introduction to brake system. So let me quickly take a look at what's going on in week 7. I think we have done the transmission matching portion, a part of it today. Okay. So I think these questions you should be able to solve after today's discussion. They are pretty similar. Then we will just move on to the, I did not go to video, to the brake system. So if we take a look at week 7 and week 8 would discuss the components of the brake system, right? And week 9 would also discuss their brake and anti-lock brake system. So what I'm planning to do is we can go much deeper into anti-lock brake system, since that happens to be uh, Ronak, I did not understand what you said. Can you repeat? Can you go to slides again to copy? You want to make note of it? The solutions will be sent out if you go here and if you click on the problem solving session, you will be given a link to Excel sheet. Okay, click here to view. So this Excel sheet will have the YouTube video link for this as well as the file I have written down today. I will upload it after this class. You can download it from there. Okay, yeah. So today we discussed transmission matching and also I think we are kind of set for week 7 in terms of problems. Next set of component we are covering is week 7, 8, 9 as and even 10 as breaks. So we will to spend some more time on discussion of anti-lock brake system, and I think in this we can take little more deeper look at the anti-lock brake system functioning. Okay, so next week we will start discussing more on ABS and stuff and braking. So do we have any more questions? Uh, Ronak, do you have any questions since you are the only person here today?
Hello,
Ah, yes.
hello.
I can hear you.
Yes, for that question problem.
Sorry, I can't hear you. Can you talk again or maybe?
Hello,
Yes.
hello, sir.
I can hear you.
So can you hear me? So for that problem for four-speed gearbox,
Uh-huh.
so that NT2, you said NT2 is equal to kg NT1, right?
Wait. Yeah, yes.
Yes,
And
yeah, for that, sir.
so
Then NT4 is equal to kg NT3, right? How it is NT1?
okay, let me.
NT4 is equal to kg NT3, right?
So kg we defined as NT4 by NT3, right?
Yes.
Yes. So okay. You are saying I should have been dividing it
So,
here rather than multiplying.
so, no, no. So then you wrote that NT1. So I didn't get that part. So why you wrote NT1 over there?
Where here?
The kg is equal to cube root.
Yes.
Yeah,
Oh,
down. Yeah.
yeah. This
The kg
step
is
you
equal
did
to
not get.
cube.
Okay. So this is fine, right?
Sir.
Okay. So let's see. What is this now?
Yes, sir.
Okay. So let us write then equals to NT3 by NT2 also, right? Let me move these things. Okay. Equals to NT2 over NT1. Okay. So what should we do? We know this definition for kg, right? So let me write NT4 equals to kg into NT3, right? Using this bit. Okay. Now what is NT3? NT3, I can take this NT2 and multiply with kg. So kg, this previous one multiplied by kg into NT2. Now what is this NT2? We can write it as kg into NT1. So we have kg square here into kg and T1. So this essentially means NT4 is equals to kg cube into NT1, right? Which is the same expression as this cube root.
Ah, okay, sir. Got sir.
Okay, great, thanks.
What you have wrote now? I just want to write this only.
Okay, any more questions?
No, sir.
Okay, so we are about to close, but if you have any questions on driveline and transmission, we can uh, take those questions. Yeah, so next week we will start discussing on the introduction to brake system. We'll slowly go through each of those aspects and move on to the anti-lock brake system. Okay, we'll show some research work done at IITM for the brakes segment. Okay. So,
Excuse me, sir.
yes, yes.
Sir, actually, I have a question about knocking off engine.
Okay.
Actually, I wanted to ask that is knocking and detonation same terms? Can we use them interchangeably, or is there like any specific difference between those two terms?
So knocking versus detonation, right?
Yeah.
Okay. How do we define detonation? One second. Okay. So what I can understand is detonation refers to spontaneous combustion of uh, the remaining air fuel mixture. Okay. After the ignition, wait, hold on. Yeah. So engine detonation refers to spontaneous combustion of the remaining air fuel mixture after the normal spark ignition is completed. So detonation may lead to knocking because knocking requires or knocking happens when there are two flame fronts which are uh, in opposition to each other. In such a situation, uh, the two wavefronts would collide and result into the phenomena we define as knocking. So, if I were to think with you here, I can say that engine detonation may lead to knocking, but not necessarily, right? So, I mean, I would see it that way. Yeah, we have. Do you have any more questions? I hope I was able to answer that.
So actually, I feel it is something like when the fuel mixture has been burnt, and
Uh,
if there is any like fresh fuel mixture left, still left after the ignition,
right.
if that burns, and that is detonation.
Yeah, that's what. So, right. But if detonation essentially is the spontaneous combustion of the leftover mixture, right? That's what you said, no?
Yes, leftover mixture only
Huh.
means that after ignition, if there is still any uncombustible fuel left in the combustion chamber.
Right. So think of it this way. Uh, if the combustion results in colliding flame front, we can call that as knocking, right?
Yes, yes.
So logically thinking, I can uh, say that engine detonation may result in knocking,
Or may not.
or may not. Right.
Yeah.
That depends on at what time that happens. Right. How is the situation at the flame fronts?
Yes, yes. Okay, I got it.
Okay, great. Yeah. Any further questions, or if not, maybe we can close. Okay. So, all right. I thank you for joining, and happy Holi. I'll see you next week. We'll start discussions on brakes.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.